Hello and welcome. In this video, I'm going to try to explain what definite integrals are. And this is something that, well, it's possibly one of the most complicated concepts from beginning calculus. And it's something you usually learn about somewhere in the second half of a beginning calculus class, after you've learned some other calculus concepts like limits. Now, I'm going to try to make this video as widely accessible as possible, so that even if you haven't studied any calculus before and you're just curious about this, it will still make as much sense as possible. But there will be a couple of spots where I will have to refer to limits or other concepts that would mean a lot more to you if you'd studied calculus already. I hope that even if you haven't studied any calculus, you can still understand the gist of what I'm trying to say here. So, on the left, we have, in general, what definite integrals look like. And on the right, we have one specific example of a particular definite integral. So let's look at what it's made up of. You have this sign here that looks like a long stretched out letter S. That's the integral sign. So whenever you see that in front of something else, it means the integral of. And it's not just a coincidence that it looks like an S. There's a reason for that, which we'll be getting into. An integral is, in a sense, like an infinite sum. So you can think of that as an S as in sum, S-U-M, like what you get when you add a bunch of things together. The A and the B stand for numbers, and those are called the limits of integration. And here we're using the word limits in just the ordinary sense of something you don't want to go beyond, the boundaries, like a time limit or a speed limit. They're not the same kind of limits as what we usually mean in calculus when we talk about the limit as x approaches something. So in this particular example, the limits of integration are 0 and 3. And that means that we are considering x values that are between 0 and 3. We are integrating over the interval from 0 to 3, that particular section of the number line, or the x-axis. Now, the function that we want the integral of is called the integrand. So in my particular example over here, the integrand is the function 9 minus x squared. And then the dx on the end is the differential. Every integral should have a differential at the end, kind of like every sentence has a punctuation mark, a period or something at the end. And the variable here, the dx, should match the variable in the function. So you might have a function of t, like 9 minus t squared, and then you would have a dt at the end. So what does this mean? What does it mean when we have something like the integral from 0 to 3 of 9 minus x squared dx? Well, first let me tell you something that it doesn't really mean. Some people who have studied some calculus have a somewhat wrong idea about what this means or how it's defined. What they think it means is, well, before I tell you what they think it means, I should probably give a spoiler warning here. If calculus were a movie, what I'm about to tell you should come as a big reveal at the end. Like if you learn that two characters in the movie that you thought were unrelated turn out to be brother and sister, or father and son, or really the same person but in disguise. So if you knew going in that those two characters were related, it would spoil the surprise twist. Of course, calculus isn't really a movie, and so I'm not really worried about spoiling a surprise, but if I were, I would not mention what I'm about to tell you next, because it would be like introducing a character by telling you how they're related to another character that you first meet in a totally different context. So, with that in mind, here is what some people think this sort of thing means. They think it means, okay, take the antiderivative of this function, like in this example, the antiderivative of 9x minus, or 9 minus x squared would be 9x minus 1/3 x cubed, then plug in those limits of integration, plug in the 0 and the 3 into that antiderivative, and then subtract to get the value of that definite integral. So if you haven't studied calculus before, don't worry about this. You are allowed to pretend you've never seen this before. But if you have seen this before, this turns out to work because of the fundamental theorem of calculus. But it's not how the definite integral is defined. It's not what this is defined to mean. Instead, there's a theorem that says, well, it turns out that you can actually evaluate it that way and get the answer that agrees with what it is defined to mean. So, what does it mean? Well, sort of what it means is take the sum over all the different x's from 0 to 3 of 9 minus x squared times dx. That is, take each of the infinitely many real numbers between 0 and 3, plug each one into 9 minus x squared, and then multiply the value you get each time by this infinitesimally small dx, and then add them all up together. Now, does that really make sense? No, not really. What does it mean to add together infinitely many things and work with things that are infinitely small? So we have to reformulate it in a way that it does make sense. But before we do that, let me give you an example of why you might want to do such a calculation and what it would represent. Suppose that starting at 1 o'clock and ending at 5 o'clock, you are driving at a constant speed of 60 miles per hour. How much distance do you cover? Well, remember, your distance is just the rate of speed times the amount of time. Miles per hour times hours. So in this case, that would be 4 hours times 60 miles per hour means you cover a distance of 240 miles. If you're going 60 miles per hour, you go 60 miles the first hour from 1 to 2 o'clock, 60 miles the second hour from 2 to 3 o'clock, 60 miles the third hour, and 60 miles the fourth hour for a total of 240 miles. Now, what if you weren't going at a constant speed? What if from 1 o'clock to 3 o'clock you drive at 75 miles per hour? And then from 3 o'clock to 3:30, you're stopped. You're going 0 miles per hour. And then from 3:30 to 4 o'clock, you drive 30 miles per hour. And from 4 o'clock to 5 o'clock, you drive 60 miles per hour. Now, how much distance do you cover altogether from 1 to 5 o'clock? Well, the answer is, first you spend 2 hours going 75 miles per hour, and you cover a distance of 150 miles. Then you spend half an hour going 0 miles per hour, and you cover 0 miles. Then you spend half an hour going 30 miles per hour, and that takes you 15 miles. And then you spend 1 hour going 60 miles per hour for 60 miles. So your total distance is 150 plus 0 plus 15 plus 60, 225 miles. Now, this particular example is unrealistic because you can't really go instantaneously from 75 to 0. If you're going 75 miles per hour and then the very next instant you're going 0 miles per hour, that's kind of a problem. You're going to go through the windshield or something like that. You can't even instantaneously go from 30 up to 60. You got to rev up to it. So, what if from 1 o'clock to 5 o'clock you're driving, but your speed may be changing from moment to moment? All you know is at any given instant in time, there's a particular speed or velocity that you're traveling at that instant. So you can think of your velocity as a function of the time. At any time, you're going v of x miles per hour at that particular instant. And that can change from one moment to the next. So how can we work out from that velocity function the total distance that you travel from 1 o'clock to 5 o'clock, from when x equals 1 to when x equals 5? Well, the idea is we could divide that whole time interval from 1 to 5 o'clock up into a whole bunch of very short time intervals of 1 second each, or 1 millisecond. And if we make them short enough, there isn't enough time for your speed to change during that 1 millisecond interval. So we can treat it as if you're going one particular constant speed just during that one particular interval. And the distance you cover during that short interval is that speed times that short amount of time. Then add up all the distances that you covered during all of those little tiny short intervals of time to get the total distance that you traveled during the whole time from 1 to 5 o'clock. So that's kind of the idea behind what we're doing here. Now here's the geometrical interpretation. Here's how to picture what a definite integral is giving you. Geometrically, it's going to represent what's usually described as the area under a curve. So suppose we have a function, f of x, and a closed interval from a to b. The interval from some number to some other number. And for now, let's assume that our function is continuous and positive value, that is, it gives you a value greater than or equal to 0 in this interval. Now, these conditions aren't necessarily required for definite integrals in general, but they are necessary to match the pictures I'm going to be showing you. The graph of the function is going to look all in one piece, so continuous, with no holes or gaps, and it's not going to go below the x-axis. So the y values are all going to be 0 or greater, putting the points on the graph at or above the x-axis. Then the definite integral from a to b of f of x dx would represent the area of the region under that curve. That is, between the x-axis and the graph of y equals f of x. So vertically, you go from the x-axis up to the graph of the function. And horizontally, you start where x is the bottom number, and you go over until you get to where x is the top number. So you're limited by those limits of integration. So we want to know, what is that area? And if the area were, say, 12, that would mean that that region, whatever shape it is, takes up exactly the same amount of space as 12 unit squares, 12 of those little squares on the graph paper. It would require the exact same amount of paint to paint it as it would, say, a 3x4 rectangle that would also have an area of 12 square units. So one example, one really simple, basic example to give you the idea, suppose our function is the constant function f of x equals 3. So no matter what you plug in for x, you always get 3 out for f of x. So the graph of that function is just a horizontal line that goes right straight across. And suppose the interval we're considering is the interval from 1 to 6. In that case, the area under the curve, the area between the x-axis and the graph of that constant function, would look like this. It would just be a rectangle. The width of that rectangle would be 5 units. And notice that comes from 6 minus 1. To get from where x is 1 to go to where x is 6, That's a distance of 5 units. And the height of the rectangle is 3. And that comes from f of x being 3, so your y coordinates are all 3, and you go from where x is 0 up to where, or from where y is 0 up to where y is 3. So the area of that rectangle is 15 square units. And so we would say that the integral from 1 to 6 of the function 3 dx equals 15. Another example, suppose your function f of x equals 2x, and your interval is the interval from 0 to 3. In that case, the region under the curve, that is between the x-axis and the graph of that function, would look like this. It would be a triangle. And if you know the formula for the area of a triangle, 1/2 times the base times the height, you can calculate that for this triangle, that would be 1/2 times 3 times 6, which works out to 9 square units. So in this case, the integral from 0 to 3 of 2x dx equals 9. Now what if your function is f of x equals 4 minus x squared, and your interval is the interval from 0 to 2? The area would be, well, I don't know. We're talking about this region here that I've shaded in pink. But it's not just a simple geometric figure like a rectangle or a triangle, though we have a nice simple formula for the area. So what is that area? Well, one thing I can say for sure is that it is less than 8, because that region fits entirely inside this rectangle that's 2 units wide and 4 units tall. So that entire rectangle would have an area of 8 square units, and the part that's shaded in pink is only part of that, so it's less than 8. But it is more than half of that rectangle. If we divided it in half, we get all of the bottom half and then part of the top half. It sticks out a little past this triangle here. So half of the rectangle would have area 4, and so this must be more than that. So the area, we don't know exactly what it is, but it's somewhere between 4 and 8 square units. So the integral from 0 to 2 of 4 minus x squared dx would be whatever that area is. And like we just said, we don't know exactly what it is, but it's somewhere greater than 4 and less than 8. Now, suppose we slice it up into a bunch of thin slices, a bunch of skinny rectangles like this, where the height of each one of those skinny rectangles is approximately the height of the curve, how far up you have to get to a point on the curve there. If we could, well, each skinny rectangle would have an area that we could calculate by taking its width times its height. And then if we add up all the areas of all those skinny rectangles, the sum that we get should be close to the total area of the region under the curve. The height of each one of those rectangles would be the value of the function. 4 minus x squared gives us our y coordinate, so that's how far up we go to get to a point on the curve. The dx would represent the tiny width of each slice, and then by multiplying those together, the height times the width, we get the area of each slice or each rectangle. And then the integral from 0 to 2 means to add up or take the sum for all x's from 0 to 2 of all of those thin slices to get the total area. Now, the sum of the areas of all those skinny rectangles is not exactly the same as the area of the region under the curve, because the rectangles have bits that stick out a little bit above the curve, and also bits that they miss, bits underneath the curve that aren't included in those skinny rectangles. So by adding together the areas of all those rectangles, we don't get exactly the area under the curve, but it's pretty close. if we make the rectangles skinny enough, it won't make much difference. There won't be very much of them that sticks out or that doesn't get included. And the narrower we make them, the closer we get to the actual area under the curve. And if we could somehow make them infinitely narrow, we might think there is no difference at all. If we make them infinitely narrow, nothing's going to stick out, nothing's going to be left over, and we'll get exactly the area under the curve. Well, to start with, let's not make them infinitely narrow. Let's just make them fairly narrow. Let's divide the interval from 0 to 2 up into 4 pieces, 4 subintervals. So we have from 0 to 1/2, that is from 0 to 0.5, and then from 0.5 to 1, and then from 1 to 1.5, and then from 1.5 to 2. So 4 subintervals, each one serving as the base of one of these narrow rectangles. And for the height of that rectangle, we're going to calculate that by taking the left endpoint of each one of those subintervals and plugging it in for x to get the y-coordinate at that left endpoint. So for the first interval, the left endpoint is 0, and if I plug 0 in for x, I get 4. So we go all the way up to 4 and take that as the height of the first rectangle. For the second subinterval, the left endpoint is 0.5 or 1/2. So I plug that in for x and I get 3.75. So if I go up to that point on the curve, it's at a height of 3.75, and so we take that as the height of that second rectangle. For the third rectangle, we plug in 1, we get a height of 3. For the fourth subinterval, we plug in its left endpoint 1.5 and get the height of that rectangle to be 1.75. Then for each of those 4 skinny rectangles, we take its height times its width, and the width of each one is going to be 1/2 or 0.5 to get its area. So 4 times 1/2 is 2, and 3.75 times 1/2 is 1.875, and so on. Then we add those 4 areas of those 4 individual rectangles together to get the total area contained in those 4 rectangles, and that turns out to be 6.25. Now that includes some bits that stick out above the curve. So the area of the region strictly underneath this curve is a bit less than that. So the area we're looking for is a little less than 6.25. Now here I got the heights of the rectangles by plugging in the left endpoint, the x-coordinate of the left endpoint of each subinterval. But if instead I had plugged in the right endpoint, like 0.5 for the first interval, 1 for the second, 1.5 for the third, and 2 for the fourth, then I would have gotten these rectangles with these heights. And so the area of each rectangle is its height times its width. And if I add those 4 areas together, they add up to a total area of 4.25. And that's a bit smaller than the actual area under the curve, because the rectangles all fit entirely underneath the curve, but there's some space left over that we didn't count. So the actual area is somewhere between the first set of rectangles that added up to 6.25 and this set here that adds up to 4.25. Now here we divided things up into 4 subintervals. We could get a better estimate if we divide it up into, say, 5 subintervals. So in that case, they might go from 0 to 0.4, from 0.4 to 0.8, from 0.8 to 1.2, from 1.2 to 1.6, and from 1.6 to 2. The whole thing goes from 0 to 2. It has a width of 2 units. And I divided it up into 5 equal pieces, so the width of each piece was 2 divided by 5, which was 0.4. If I take the height of each piece by plugging in the left endpoint of each interval for x, That gives me these rectangles shown here. And then take the height times the width to get the area of each rectangle. Add them all together. They add up to 6.08. So that's the total area of these 5 rectangles that are a little bit more than what's under the curve. If I use the right endpoints to plug in and calculate the heights of the rectangles, they would fit underneath the curve. I would get a total area of 4.48. So now I've narrowed down the area under the curve to somewhere between 6.08 and 4.48. I can narrow it down further by dividing this up into more subintervals that are narrower. If I divided it up into 10 pieces, so like 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, and so on, then plug in the left endpoint of each of those subintervals, 0, 0.2, 0.4, and so on, to get the height of each rectangle. Multiply the height times the width, which in this case is 0.2 for each one. Add those together, the sum is 5.72. If I use the right endpoints instead, the sum turns out to be 4.92. So now we've narrowed it down further. The actual area under the curve itself is somewhere between 5.72 and 4.92. And we could keep on going like this. We could divide it up into even narrower subintervals. So using 20 subintervals, 0 to 0.1, 0.1 to 0.2, and so on, the so-called upper sum that we get by using the left endpoint, so that gives us the rectangles that stick out above the curve, gives us a total area of 5.53. And the lower sum, using the right endpoints, gives us 5.13. So it's somewhere between 5.53 and 5.13. Now, if you're familiar with the calculus way of doing things, you might anticipate where we're going with this. You might think, oh, now we're going to take the limit as the number of subintervals, that is the number of little pieces that we're slicing this up into, approaches infinity. Well, that's sort of the general idea, but it's actually a little more complicated than that. So, first, let's look at some terminology. Okay, so a partition is a particular way of dividing an interval up into subintervals. So in the example shown here, we've taken the interval from 0 to 2 and divided it up, partitioned it up into 4 subintervals. The dividing points are here at 0.5 and at 1 and at 1.5. So the 4 subintervals are 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. So that's one particular way of taking the interval from 0 to 2 and partitioning it up into subintervals. In this case, 4 of them. And then here we partitioned it up into 5 subintervals, each with width 0.4. Now, the subintervals in a partition do not necessarily need to be all the same size. You can make some of them wider than others. So here's an example where I partitioned the interval from 0 to 2 up into from 0 to 1, and then 1 to 1.25, 1.25 to 1.5, 1.5 to 1.75, and 1.75 to 2. So now that first piece is a lot longer than all of the others, but that still counts as a legitimate partition of the interval from 0 to 2. And then we define the norm of a partition to be the length of its longest subinterval. So in this example, the longest subinterval is the first one, the one that goes from 0 to 1, which has a width of 1. All the others are shorter than that, so the norm of this particular partition is 1. And here, don't worry too much about the notation, but we're using the triangle-looking thing, the delta, to stand for the partition itself, and then by putting that between those double lines, we mean the norm of that partition. Now, in a regular partition, one where all the subintervals are the same width as each other, then the norm would be just that width. It would be the width of the entire interval from the right endpoint minus the left endpoint divided by the number of pieces you divided up into, b minus a over n. So in this example, that would be 2 minus 0, or 2 for the whole thing, divided by 10 for how many pieces we divided up into. Now, why not just make all partitions regular partitions? Why do we allow the subintervals to be different lengths? Well, either it matters or it doesn't. In where we're ultimately going with this, what we're going to end up with as our final result, if we would end up with that same final result no matter what kind of partitions we use, whether or not they are regular, then we may as well allow as much freedom as possible in choosing those partitions. And if it did make a difference, and we did end up with different final results from different kinds of partitions, we'd want to know that. And we'd have to worry about which result counts and why. So we are allowing the partitions to be any way of dividing an interval up into subintervals. Now, once we've chosen a partition, we want to choose one number from each subinterval at which to evaluate the function, and therefore find the height of the approximating rectangle. So the number we choose from each subinterval could be the left endpoint of that subinterval, like 0 and 0.4 and 0.8 and 1.2 and 1.6. Or it could be the right endpoint of each subinterval, like 0.4 for the first, 0.8, 1.2, 1.6, and 2. Could be the midpoint right in the middle of each subinterval. So it could be 0.2 and 0.6 and 1 and 1.4 and 1.8. Or it could be some other number kind of randomly chosen from each subinterval. And we are seeing slightly different sums for different choices, different ways of picking an x from each subinterval to plug into our function. But the smaller the subintervals are, the less of a difference it makes which x we choose from each subinterval. In a sense, we're going to be shrinking the subintervals down to 0. And then, once we do that, again, either it will matter which x's we choose, or it won't. If we get the same final answer, no matter which x's we choose, we want to allow as much freedom as possible. But if we get different final answers from different choices, we need to worry about that. And in fact, it turns out that for most functions, as long as they're reasonably well behaved and don't get too weird or messed up, then it doesn't matter. We do, in fact, get the same final result no matter how we choose our partitions or our x's. Now, for each subinterval in our partition, multiply the value of the function at the x point that we chose from that subinterval by the width of that subinterval, and then add these all together. And this is called a Riemann sum. Now here I'm using delta x sub I to stand for the width of the ith subinterval. Delta x sub 1 would be how wide the first subinterval is, delta x sub 2 would be how wide the second one is, and so on. And I'm using c sub I to stand for the particular number that you chose from the ith subinterval to plug into the function in place of x. But the notation I'm using is not really important, and different people use different notation here, so don't worry too much about that. We just took over all the subintervals that we partition things up into. We plug a number from each subinterval into the function to evaluate it there, multiply that by the width of that subinterval, and then add all of those together for all the different subintervals in our partition. So that is a Riemann sum. And all of these sums that we've been seeing are examples of Riemann sums. They are examples of, we partitioned the interval from 0 to 2 up into subintervals. We chose an x from each subinterval to plug into the function 4 minus x squared. And then we multiplied that value times the width of that subinterval and added all those together. So that's what we call a Riemann sum. Then we take the limit of these Riemann sums as the norm of the partitions approaches 0. If this limit exists, we say that the function f of x is integrable on the interval from a to b, and we define the value of that definite integral, the integral from a to b of f of x dx, to be whatever this limit is. Now, this is something that if you haven't studied calculus, you're not going to understand what a limit is, but basically it means that if we've got an integrable function, these Riemann sums are always going to get arbitrarily close to some particular number once the norm of the partition gets close enough to 0, meaning all the subintervals are sufficiently narrow, regardless of exactly how you choose your partition and exactly how you choose your x's from the subintervals. Now, this way of defining definite integrals is called the Riemann integral. Riemann sums and the Riemann integral were named after this guy, German mathematician Georg Bernhard Riemann, who lived in the middle 1800s. And this way of defining definite integrals is what you'll see in most calculus textbooks. Now, there are other more powerful but more complicated ways of defining integrals. If you thought this was complicated, there are even more complicated ways of doing it, like what's called the Riemann-Stieltjes integral or the Lebesgue integral. And these are things that I didn't even hear about until I got to graduate school. So they are very advanced. You may not ever need to worry about them. In fact, you may not need to worry about all the gory details of how Riemann integrals are defined. But somebody had to worry about that to make sure that things really do work. But it can be proved that if your function is continuous on the interval you're looking at, if it doesn't have any place where it's undefined or does anything weird, it must therefore be integrable on the interval from a to b. So if it's continuous, it must be integrable. If it's not continuous on that interval, it might still be integrable there. So it's not really difficult for a function to be integrable. It's not really difficult for a definite integral to be well defined and have a particular value. Now, in practice, definite integrals are almost never evaluated directly from the definition. That is, by finding the limit of Riemann sums for a particular function on a particular interval. That would get really messy and complicated to try to work that out for a particular function and a particular interval and work out rigorously what that limit turns out to be. So in practice, particular definite integrals are usually evaluated using either the fundamental theorem of calculus, which is what I was talking about way back earlier when I said, okay, this is a spoiler alert. This is what some people think this means. Well, it's not what it really means in the sense of it is defined that way, but it turns out that in many cases, you can evaluate it that way. So they're usually evaluated using that fundamental theorem of calculus, or they are approximated by calculating something like Riemann sums. Not the limit of the sums, but just some actual Riemann sums or something similar to that for a fairly narrow partition. So divide the interval up into subintervals and do some calculations, and that's what's called numerical integration. So if you have a programmable calculator or a computer app or something like that that will evaluate definite integrals for you, there's a good chance that what it's really doing is doing a lot of number crunching and calculation and calculating a bunch of Riemann sums or something similar to that to come up with the value of the definite integral. So that's my attempt at explaining what definite integrals are. Hope you found that helpful or interesting. Thanks for watching.